Jumping into question 5, we've been given a trig expression that we've got to simplify without using a calculator. So I'm going to tackle it bit by bit. Now this over here I want to set up for reduction. So I'm going to add 360 to make that possible. And after I add 360, I want to put the 360 in front of the minus x so that it starts to look like this. And then that's going to set me up beautifully to use my little cast diagram. Let's grab him while we're here. Alright, so the purpose of doing that was to set myself up for reduction, because that's now in the 360 minus quadrant. Now sine of 90 plus x is a co-function that you must be comfortable with and know off by heart. So a trigger to recognize co-functions is when you see 90 plus. Now that one is this co-function over here. Sine of 90 plus an angle is just equal to cos of that same angle. So this over here will change to cos of x. Okay, now the sine 2 of x, it is a double angle, I do recognize that, but I don't know what to do with it just yet, so I'm going to sort the bottom out first maybe, and then afterwards I'll expand that. So let's leave the sine 2 of x there. Okay, now I'm going to sort out the bottom. 360 plus x, that's not in our reduction diagram. So what we're going to do is subtract 360 to make this normal. And 360 minus 360 is just 0. So this 360 essentially just disappears, and we're left with 2 cos x at the bottom. Okay, now we're going to start to tackle them individually once again. So tan of 360 minus x is inside the 360 minus quadrant. And in the 360 minus quadrant, only cos is positive, which means tan will be negative. So this will change into negative tan of x. This cos x is simplified as far as possible, so I'm just going to leave it there for the time being. And now the sine 2x, I'm going to expand with double angles. If you see 2x, that's your trigger to think of double angles. Okay, now sine 2x only has one double angle, so we're going to expand it with this guy down here. Okay, and when we expand it, instead of having a theta, we've got an x, so these will just become x's. So let's go ahead and expand it. And this 2 cos of x is simplified as far as possible so he can stay behind. Okay, now we're going to start to work through it individually again. Now this minus tan x, I smell an identity over there. I can change tan x to sin x over cos x, and you've got to know that off by heart. What I do to remember this trig identity, tan theta equals sine over cos theta, I say tan your socks. Tan equals sine over cos. SOC, socks. I know it's a bit weird, but it works for me. Okay, this negative will just stay in front of the sine over cos, like so. So that negative doesn't get affected as we discussed. This cos x will stay over here. Okay, now I can start simplifying this fraction. How satisfying. The 2's will cancel with each other because I've got one term over one term. So I am allowed to cancel. And additionally, the cos x's will cancel with each other. What a dream. So after that, we're left with sin x over 1, which is just sin x. Alright, this thing is starting to look a bit simpler. Now I can also cancel things over here, and quite a nice way of seeing it is this cos x, I can put it over 1, and after I do that I can cross cancel with these two fractions. So I can cancel the causes over here, and after I cancel the causes I'm just left with minus sin x over there. And then I've got minus sin x plus sin x, which will give me a crispy little 0. It's like saying minus 7 plus 7. It's 0. Geez, all that hard work for a crispy little 0. Okay, you see, this question tested quite a lot of things. Reduction, cofunctions, double angles, identities, a bit of algebraic fractions at the same time. Okay, let's have a look where our 6 marks will come from. The first mark comes from the cos x through the use of cofunctions. The second mark comes from simplifying this into this by subtracting 360. The third mark comes from the tan x through reduction. The fourth mark comes from expanding the sine 2x to that, using your double angle identities. The fifth mark comes from changing the minus tan x to minus sine x over cos x with the use of trig identities that you should have learned in grade 11. And the last mark comes from the final answer of 0. Question 5.2, they tell us that sine of 27 degrees equals p. And without the use of a calculator, we need to get the following things in terms of p, or the following trig ratios in terms of p. So if you see this, sine of an angle equals a letter, you grab that thing and you start off like this. We firstly change this p to p over 1, like so. And then we're going to use the classic SOHCAHTOA. Okay, so in this particular case, we've got sine. Sine is opposite over hypotenuse. That's what SOH is a shortcut of remembering. So the entity on top here will be the opposite side of the triangle, and the entity at the bottom here will be the hypotenuse of the triangle. And now we're going to set up a sketch that reflects that. And 27 degrees falls in the first quadrant of the Cartesian plane. So our sketch is going to be in the first quadrant. So let's get a Cartesian plane going and set up our sketch. And now we're going to draw the triangle in the first quadrant. You know, I always used to get confused. Do I draw the triangle like this? Or do I draw the triangle like this? And the bow tie helps you remember how to draw it. So this little shape here is called the bow tie because it resembles the shape of a bow tie. And we can see if we're in this quadrant, we draw the triangle like that. So over here, I'm going to draw the triangle like that. And when I draw the triangle, the 90 degree slit sits snug over there. And then this 27 degrees is always the one closest to the origin over here. So I'm going to label this 27 degrees. Okay, now before we start labeling the sides, it's always worth our time to get this angle over here using interior angles of a triangle. This plus this angle will give me 180 degrees. So if I just say 180 minus 27 minus 90, it will tell me the size of this angle here. So let's go ahead and do that on our calculator. So we just pop that in, press equals, and we get 63 degrees. And then I like to put that in the corner here. And check at this, the next question, there's a 63 degrees, so you're more than likely going to be tested on it in most instances. Okay, now we're going to start to fill in the sides of the triangle. So this P is opposite. Now you may be wondering, opposite to what? It's opposite to this angle over here. It's all relative to this angle. So P is opposite the 27 degrees. Opposite the 27 degrees will be this side over here. So that's P over there. And the hypotenuse, this 90 degree angle always points to the hypotenuse. So this length of the hypotenuse will just be 1. And then to get the missing side in the triangle, we just do Pythag. So the Pythagoras theorem states my hypotenuse squared, so 1 squared, is equal to this side squared plus this side squared. So it's going to be p squared plus, and I'm going to call this x squared for now. So now the mission is to get x on its own, so we know what this side is. So 1 squared is just 1. I'm going to move this p squared over to that side of the equation, and it becomes minus p squared. And then I need to get rid of the square on x, so I square root both sides like so. So square root the side and you just get x. If you square root the side, the square root just stays over this binomial. So now I've got to replace that x with this big square root. And now I'm finally ready to answer the question. So cos of 27. Cos is equal to the adjacent over the hypotenuse. Adjacent just means next to. So adjacent to the 27 or next to the 27 is the 1 minus p squared under the root. So we put that on top. And at the bottom will go the hypotenuse. The hypotenuse is 1, so we just put 1 at the bottom. And anything divided by 1 just kind of stays the same. Like 7 divided by 1 is just 7. So we can simplify this to just the root. And now we've successfully answered the question. Cos of 27 degrees is equal to the square root of 1 minus p squared. You can also do this with the use of identities, but I found the sketch is a bit better. So let's see where our 2 marks come from. First mark comes from the correct diagram, and the second mark comes from the final answer. Alright, now 5.2.2, we need to get sine squared of 63. The square is a bit off-putting, so how you deal with it is like this. You just move it to the outside. These are essentially the same thing. They mean the same thing. If the square is there or on the outside, it's the exact same thing. Now that I've got sine of 63 inside the bracket, I'm going to use my sketch to change sine of 63 to the actual ratio. So let's grab SOHCAHTOA and make that happen. Okay, so we're working with sine, so we're going to be using SOH. Sine is opposite over hypotenuse, and it's opposite to this angle. So now we're using 63 as the reference angle. Opposite 63 is this thing over here, so I'll put that on top. And what goes at the bottom is the hypotenuse. The hypotenuse won't change no matter which angle you're looking at, so the hypotenuse is still 1. And remember, like the last question, 7 over 1 is just 7, so this over 1 just kind of disappears. And after we've simplified that, this square cancels out with this big root, and we just left with what's underneath the root, the 1 minus p squared, as our final answer. And last but not least, your 2 marks come from the answer only in this question. Okay, welcome to your challenge round. Your challenge round is 13.5. We need to get cos of 13.5, but I don't see an angle of 13.5 anyway, so this is a bit weird. What I do notice is 13.5 or 13.5 is half of 27, or you can see it as 27 is double the size of 13.5. Double angles. We've got to use a double angle identity to get this thing. So let's have a look at our double angles. So we've got 4 possible double angle formulas that we can utilize, but it's very specific as to which one we need to choose. I don't want one with sine in it, because I won't be able to get like sine of 13.5, and I need cos of 13.5. So I'm going to choose this double angle over here. And I'm going to show you how we utilize this double angle to get this. Okay, so cos of 2 theta, I'm going to model this to be 27. Because then this theta will be half the size of 27, which is 13.5. And then I'm going to use the sketch to change this cos of 27. Or in fact, I think we actually got it earlier. Yeah, here it is. Cos of 27 is this thing over here. So let's change cos of 27 to the square root of 1 minus p squared. And after we make that change, the mission is to get this cos of 13.5 on its own. So how we start doing that is we move the negative 1 over and it becomes plus 1. After I move that over, I want to get rid of this 2 by dividing both sides by 2. These 2's will cancel, and then I'm just left with this big mess. I cannot simplify that at all. And then there is one last thing left to do. I need to get rid of the square, so I square root both sides. And what that entails is if I square root this side, the square disappears. And if I square root this side, I just put a massive square root over this thing, because I can't simplify it. So there lies our final answer. Yes, this question was a bit of a parked down prawn, bro. Okay, let's have a look where our 3 marks are coming from. The first mark comes from using this double angle identity. The second mark comes from the substitution of cos of 27 into the double angle identity. And the last mark comes from your final answer. In question 5.3, we've been given this trig expression is equal to k, and we need to express this in terms of k. Now, I smell a compound angle over here. Your trigger to see it is if you see a binomial, that is the angle, and you can't simplify it further. So let's grab our compound angles. So to select the appropriate compound angle, I have a look here. It's cos of an angle minus an angle. So I need to find that on the left hand side here. It looks like it's the last one, cos of an angle minus another angle. So I'm going to get rid of the others and just focus on this one. So let's utilize this compound angle for this specific scenario. So I'm going to expand this using this. And let me show you how you accomplish that. Okay, so I'm not working with a and b, I'm working with x and 45. So I'm going to replace this a with x and this b with 45, and that's going to trickle into this side as well. And you can see I've made the necessary replacements. A has been changed to x and the b's have been changed to 45s. Now I smell some special angles here. 45 is a special angle. So we're going to use our special angle triangles, or we can even use our calculator. We didn't get told that we can't use our calculator. So let's have a look at the special angle triangles. So this over here is our special angle triangle with the 45 degrees. We're not going to use the other triangle because we don't have 30 and 60. So we're going to use this in conjunction with SOHCAHTOA. Or, like I said earlier, we can use our calculator. I'm definitely going to use it to triple check my work. So this cos x will stay behind. And now this cos of 45, I'm going to use SOHCAHTOA with this triangle to get it. So let's grab SOHCAHTOA quickly. So if I'm using 45 as my reference angle, cos is adjacent over hypotenuse, ka. So adjacent to this 45 is root 2 and the hypotenuse is 2. So cos of 45 just changes to root 2 over 2 like this. And I like to put it in a bracket to help remind myself that I'm actually multiplying these two factors. Okay, now the sine x can stay behind, nothing happens to him. And I'm going to do something very similar with sine of 45. Sine is opposite over hypotenuse. So if I'm using 45 as my reference angle, opposite over hypotenuse, so it's also root 2 over 2. And while we're here, let's quickly check those with our calculator. Okay, so cos of 45, just press equals, and it definitely gives me the root 2 over root 2. And let's just change that cos to a sine. And also root 2 over root 2, so our special angles are solid. And now what I like to do is kind of simplify it a little bit. You don't have to, but it's a good practice to get into with maths. So I like to move the numbers to the front when I have two factors like this. It's just easier to read. It's like the normal convention. So cos x times root 2 over 2, I simplify it to this, like so. So I'm basically just rearranging it a little bit. I like the numbers first and the trig ratio second. I'm going to do the exact same thing here. Put the number first and the trig ratio second. And once I've simplified that a little bit, I smell a common factor. This term, as well as this term, have this in common. So I'm going to remove it as a common factor. Okay, so how I do that is I write it in front of a bracket. Then I analyze this term. If I took this out, there's only a cos x left over in this term. So that's what goes first inside our bracket. And now I rinse and repeat that procedure with the second term. So because my common factor is positive, this sign will stay the same. And if I analyze this term, I remove this root 2 over 2, so there's only a sine x left over. Okay, so we are getting somewhere. This looks a little bit familiar. Hey, how's it, brother? Check over there. Cos x plus sine x is the same thing as k. So I can replace this whole bracket with k, and then my job is done. And our final answer is root 2 over 2k after the replacement of this into k. And lastly, let's have a look where the 4 marks come from. Your first mark comes from the expansion with the compound angles formula. The second mark comes from the special angles, changing cos of 45 and sin of 45 to the relevant ratios. The third mark comes from factorizing correctly, and the last mark comes from your final answer. In question 5.4, we have an identity, a rather nasty one if I do say so myself. Alright, so I'm going to start with the left hand side because it looks more complicated. So let's get the left hand side down quickly. And now I'm recognizing quite a few things with the left hand side. I see a double angle there, a double angle over there, and I see a tan here. So predominantly what you want to do is you want to sort out the denominator first. I'm not going to touch this double angle until I see how this unfolds. So I'm going to change sine 2 theta into the respective double angle. So let's grab that formula quickly. And just remember, this is on your formula sheet, so you don't have to know them off by heart. And then there's only one double angle formula for sine of 2 theta. It's this bottom one, so I'm going to get rid of the others for now. And let's go ahead and change the sine 2 theta into 2 sine theta cos theta. And then this tan theta, it's a trig identity lurking about. So let me just quickly remind you of those grade 11 ones you need to know off by heart. And remember, I can change tan theta to sine theta over cos theta. I'm going to ignore these other three for now because we're not using them. And now after that replacement, we are getting somewhere. So now I want to get an LCD before I decide what to change this to. Because remember, I have 3 options in my formula sheet to change this. So I don't really know which one to change it to until I get the LCD, simplify stuff, and then I can make a much more informed decision. So the LCD will be this thing over here. And this denominator is missing 2 factors. It's missing this 2 and it's missing a sine theta. So I've got to multiply the top and the bottom by 2 sine theta to achieve that LCD. Okay, so we're just going to multiply the top and bottom by 2 sine theta as discussed. This fraction will stay exactly the same. Nothing's going to happen to that fraction. And then sine theta times 2 sine theta. 2 times 1 is just 2. And sine theta times sine theta is sine squared theta. And then at the bottom, cos theta times 2 sine theta will give us this. 2 sine theta cos theta, which was part of our plan the entire time. And now we've got both fractions over the LCD. So we kind of morph them into one fraction like this. And you want to get kind of comfortable enough to do that all in one step. So yeah, basically there's our LCD sorted out. And now I can finally make up my mind as to what I'm going to change this cos 2 theta to. So let's grab our double angles once again and make an informed decision of what we should change it to. Okay, so these are the 3 options I have available to change this cos 2 theta. And my decision is going to be based around this, what's on the right hand side. So at the end of the day, I just want sine theta and cos theta at the bottom. So I need to get rid of this 2. And to do that, I need a 2 on top to cancel. And I'm also noticing this. This looks an awful lot similar to that. And if I make the selection of this double angle, and this one's a minus and this one is a plus, they will cancel each other out. And I'll get 1 plus 1, which will give me 2, cancel with this 2, and then I've got the right hand side. So I'm going to choose the middle one. And after I replace cos 2 theta with the necessary double angle identity, we're going to watch the magic happen. Now minus 2 sine squared theta plus 2 sine squared theta, they cancel. What a dream. And 1 plus 1 is 2, so at the top we just left with 2. And now, because we have one term over one term, we can cancel the 2's with one another. And then we're left with this, the right hand side. And then there's one last thing I need to do. I just need to say equals RHS, because we need to prove the left hand side equals the right hand side. So I do have to write that. Just like that. And let's have a look where our 5 marks come from with this nasty little identity. The first mark comes from changing sine 2 theta to 2 sine theta cos theta using your double angle identity over there. Second mark comes from changing tan to sine over cos. Remember to tan your socks. Tan equals sine over cos. That's how I remember it. Third mark comes from our LCD. The fourth mark comes from the double angle identity we apply to this cos 2 theta. And the last mark comes from simplifying this, cancelling your terms to get this expression over there. And that wraps up our identity. In this question, we've been asked to get the general solution of this trig equation over here. So the first thing I see is a 90 minus. So the alarm bells are ringing for cofunctions. So I'm going to grab the list of cofunctions and let's see what we can do with it. Okay, so I see cos of 90 minus an angle. So I want to find that here, cos of 90 minus the angle will change into sine of that angle over there. So the right hand side, I'm just going to change it to sine of 2 theta. And after I made that change, the alarm bells are ringing again. 2 theta, I see a double angle. 2 times something, another way of saying that is doubling it. So let's grab our double angles. And then luckily with sine of 2 theta, there's only one double angle for it. So I'm going to use this bottom one here. And I'm going to expand sine of 2 theta into 2 sine theta cos theta. And after I've done that, this becomes a quadratic trig equation because I see a sine squared over there. So with quadratic equations, you want to move everything to one side and make it equal to 0. So what I'm going to do is move this term over to that side so it equals 0. And when I do that, it will become the minus version of itself. So it will change to minus 2 sine theta cos theta. And why I want to do that is so that I can set myself up to factorize. So now I'm going to factorize out the highest common factor. And I'm going to kind of over-explain this so that you can see it a bit better. Sine squared theta is just a shorter way of writing sine theta times sine theta. Like this. And now we can recognize the common factor a lot easier. They both have a sine theta, this term as well as this term. And they both are divisible by 2. So my HCF is 2 sine theta. And you want to kind of be able to recognize that with this just being the 4 sine squared. So I'm going to change that back quickly. And now we're going to remove the 2 sine theta as a common factor. So I start off by writing the 2 sine theta and I open a bracket. 4 divided by 2 will leave me with another 2 here. Another good way to think about it is 2 times 2 will give me 4. I removed one of the sines here as discussed earlier. So there's 1 sine theta left over. And then that sorts out the first term. Now the minus will stay in between them because my common factor is positive. So I'm going to keep the minus there. And from the second term, I removed the 2 sine theta as a common factor. So all I have left over is this cos theta. And now we have successfully factorized that into this. Now, as per quadratics, we grab each factor and work with them separately after we make them equal to 0. So this is factor 1 and this is factor 2. So I'll start off by saying factor 1 equals 0 underneath. Just like that. And then I'll put the word or in between them. And then I grab factor 2 and make factor 2 equal 0. And after I've split up my factors like that, I'm going to start working on them separately. So let's start off with this guy over here. I want to divide both sides by 2 to get rid of this 2. And when I do that, these 2's cancel, just leaving with sine theta. 0 divided by 2 is just 0. So essentially the 2 just disappears. Now there's one of 2 ways we can go from here. We can think of the graphs, use the graphs, or we can go down the rabbit hole with the reference angle, quadrant, and solutions. So I'm going to do the reference angle, quadrants and solutions just to strengthen my general solution skills. So I'll start off by getting my reference angle. I take the sine over and it becomes arc sine or shift sine. So my reference angle is shift sine of 0. And I'm simply going to lean on the calculator to help me work that out. Shift sine of 0 will give me 0. So that's my reference angle, 0 degrees. And now I've got to select the quadrants that I'm going to be working in. So I do a small little cast diagram somewhere to help me select them. And then once I've got my little cast diagram in, I look at this line, sine of theta equals 0. So you can choose either both the positive quadrants for sine or both the negative quadrants. I find it easier to work with the positive quadrants. So I'm going to go ahead and select quadrant 1 and 2. And now I'm going to get my general solution for quadrant 1. So for quadrant 1, it's going to be this angle theta always goes on the left hand side of the equal sign. So I'm going to say theta equals. And then for quadrant 1, you just put your reference angle in, and then we're going to say plus K360 because we're working with sine. And I cannot simplify that any further, so now I'm done with quadrant 1. Now I'm going to focus on quadrant 2 over here. And quadrant 2 is the 180 minus quadrant. So I'll start off the same before. This angle here goes on the left. And I'll say theta equals 180 minus my reference angle of 0. And 180 minus 0 is just 180. And then next to that, I do have to put the plus K360. Remember, sine and cos is 360, whereas tan is 180. So let's just copy paste the plus K360 next to that. And then just to finish these general solutions off, I need to state that k is an element of integers. And how we do that in mathematics is we say KEZ like this. So it's just a normal K with this weird looking E and the Z with like a double stroke over there. And I need to do it for both the general solutions. And now I've officially wrapped up the general solutions for this factor over here. So now I'm going to kind of do the same process with my second factor, but there is a bit of a trap in the beginning. Okay, so over here, what we want to do is take this cos over so that we can divide both sides by cos to get a tan. So let me show you how we accomplish that. So if we move this negative cos over, it becomes positive cos, just like that. And then we divide both sides by cos theta. And the reason why we do that is so that we can use the trigonometric identity of sine over cos is tan. And remember, you've got to know that off by heart. Okay, so this will change into 2 tan theta. Causes here cancel and just leave you 1. And now I want to get tan theta on its own. So I'm going to divide both sides by 2. So tan theta will equal 1 over 2, formerly known as a half. And after we've done that, we're going to start our process of reference angle, quadrants, and general solutions. We call that the QRS method: quadrants, reference angle, and solutions. And the beautiful thing about tan is you don't need to do both quadrants. You can just do one quadrant. So let's get a little cast diagram going. And now I look at this line and I can see tan is positive. So tan is positive in this quadrant and this quadrant. And remember, as discussed earlier, we only need to do one of these quadrants. I'm going to do this one because it's easier. So I don't even need to do this one. And we're going to start off by getting our reference angle. So if we take that tan over, it's going to be shift tan of a half. Okay, and if you know your trig functions well enough, you'll know that that's 45. But let's just check it really quickly. So shift tan of a half. It is called arctan, but I like saying shift tan so that you remember what to type in your calculator. And that gives me 26,57. And now I just need to do the general solution in quadrant 1. So quadrant 1 will just be this equals, or theta equals in this case. And in quadrant 1, I just put my reference angle, and then I'm going to say plus K180 next to that because I'm working with tan. And after I've got that down, I've just got to slap on the k as an element of integers next to that general solution, and then I'm officially done with this behemoth of a trig solution. Okay, and last but not least, let's look where these 16,000 marks come from. First mark will come from using your co-functions to turn cos of 90 minus 2 theta into sine 2 theta. Second mark comes from the expansion of this through the use of double angles. The third mark comes from the correct factors. The fourth mark comes from making each factor equal to 0. Fifth mark comes from these two general solutions, and the last mark comes from this general solution that we got through the tan.